let's start. As first, I want appreciate my sincere thanks to FABER event and to the organizers for inviting me in this very fabulous, wonderful project. So today, my presentation would be digital twins for engineering. This is a research direction currently I'm working on. Especially, I will share some of our experience about the AI-assisted digital twins for structural condition assessment and maintenance. This has a special focus on the structural integrities like fatigue or corrosion fatigue. Just a brief introduction of myself. I'm J.Heng from Sichuan University. I'm an associate professor here, and I was be a Marie Curie fellow before at University of Birmingham. And currently, I'm also working as the cross-modular leader of intelligent construction or maintenance. So let's start. Today, my presentation will cover four aspects. First, some general perspective of AI tools, especially for engineering, and then we will talk about the digital twins supported by this kind of AI tools, and then I will share with you two case studies. But I'm not so sure if there is time limitation. Please kindly remind me, so maybe we can cover the first case study, and then for the second one, maybe next time or some time else. Okay, so let's go to the general perspective for AI tools for engineering. Nowadays, AI is very popular. Every day we talk so much about not about AI every day. So what is AI by definition? Here I list the definition from ChatGPT. Actually, it's like AI define themselves. Okay, so from this definition, we say that AI is not merely programmed to follow fixed rule, rather it can make inference, act automatically or sometimes semi-automatically, and it can adapt its behavior over time in response to new data or changing conditions. It also has some key features like it has learning and adaptability. That is means learn from the data and adjust over time. Also, it can do reasoning and its problem solving. And more important is perception and also has the ability of interaction. That means it always interacting with the environment or user through perception or language understanding. Especially this is true for the current large language model, which we will talk about a little bit in the following. Also, it has the power of decision making. So sometimes it can act independently, make the decisions or generating outputs with a level of autonomy that can distinguish itself from those deterministic rule-based systems. Sometimes we also call this kind of system like computer intelligence or something like that. So together, this feature defines AI's potentials. It does more than the simple tasks. It learns, reasons, perceives, and acts. So let's get into the next slide. So what's the foundation and the function of AI? For actually, it's a multidisciplinary domain, just like an intersection between the computer science. This is the most important, and also statistics and neuroscience, and also social science. For instance, AI draws from the computer science for algorithm programming and architectures, statistics for probability modeling, pattern detection, and data analysis, and also neuroscience for brain-inspired models and learning mechanisms. This is very important, just like some very fashion AI text like a transformer that has self-attention, and sometimes we talk about the meta-learning, which is now quite popular. And also it learns from social science for understanding human behavior communication, and the most important thing, the ASIC issue of AI usage. This is quite hot nowadays. For the functions, AI has here I list four core functions. One is recognition, and then based on this, it has a congregation, and then analysis is another important feature for AI. Finally, the decision making makes AI to choose the best actions or recommendations based on the goals and the constraints. Actually, I will demonstrate the decision making in our first case study. So together, these foundations and functions highlights the AI's interdisciplinary nature and its ability to perceive, understand, analysis, and act. Okay, so how does AI work? Let's have a look at the core mechanism or how it works. At its heart, AI is about learning a mapping relation from input. Just bear me for a while. Maybe I can use the pen. Yes, just like change the color. Maybe read. Okay, we can see here, it's like a mapping from input to output. So in another word, this is like finding a function that links a question to its answer, question to answer. So we can think this process mathematically as a function. So here, just like this. Here, X is the input, and that is a question we ask AI, and Y is the output that the answer it gives. So for AI, there is some key features. First is mapping. Another thing is it's always not always is a lot of time it acts as a gray box. Well, how to say a black box where we only tell it works well without fully knowing how it works internally. Other times, sometimes it's a gray box where we understand part of the logic and design, but we just cannot have just like a comprehensive understanding about this. And also some key process for AI. First, is a training stage that we give the model lots of lower input output examples so it can learn from underlying patterns. And then comes the prediction use the AI model we trained from data. We can do the prediction, or sometimes we call it inference. Especially this is quite popular in computer science. They call it inference rather than prediction. So we can use a trained model to estimate the new output from the new input. Some key considerations about AI. Sometimes we should consider we should balance the data quality with the quantity. Having more data can help, but clear, relevant data usually matters more than the volume. Also, we need sometimes to consider the model complexity and the data complexity. That means the model needed to be just complex enough to capture the patterns in data. Otherwise, sometimes if the model is too simple, it will cause an issue of something we call the underfitting. If the model is too big, too complex than the data, it will cause the issue of the what we call the overfitting. That means you fit the noise rather than the data, the patterns, raw in the data. Okay, let's go on. Okay, so when we talk about AIs, there are three types of AIs. That is the ANI, AGI, and SI. For the ANI, we also call it as narrow intelligence, sometimes also as a narrow models. This is also called as weak AI. It focuses on specialized in solo task or narrow domain, just like Sierra or Cortana, or sometimes the AI model we produce or create or develop in our case studies, just like the case study I will talk about later. Okay, so then comes the AGI, that is general intelligence. This is also called strong AI. It can have the human level intelligence and it can transfer knowledge between tasks, just like AI agent. Just like what the OpenAI is trying to advertise now, this is that the ChatGPT 5 is now PhD level intelligence, but actually, from my understanding or my perspective, I don't think that's a full HI. It's like a pathway to the HI. So maybe I will talk about this later. And for the ASI, that is super intelligence, it can surpass the best human brains in all fields. Hopefully, we are thinking now this will come, but only will come. We cannot foresee when it will come. So, uh, for the development of AI, it's like started in 1915s, where Alan Turing proposed the very famous test that we call the Turing test, a very comprehensive experiment for evaluating the machine intelligence. And then, however, just like in 1990s, we saw the famous XOR problems exposed limitations of single-layer perceptrons, leading to the first AI winter here, because the limitations in computation powers. And then in 1990s, just like around there, we have the algorithm like the SVM that is I suppose this algorithm is by Hinton, who is recognized as the godfather for artificial intelligence. That is supported victim machines offer the very powerful classification tools. And by 2006, it's like here. Yeah, you can see the name of Hinton here. Yeah, so this here we have the deep learning, which is quite popular now, because at this stage we have very powerful GPUs and more data, and also largely thanks to pioneers like Hinton. And from this on, we just saw a blooming of different kinds of AI techs, especially just like in 2017, we saw the introduction of first transformer that is like maybe probably first is BERT, and then in 2022, it's like the introduction of GPT-3, which demonstrated the power of large-scale pre-training. And by 2023, we have the GPT-4 and GPT-4.5, which brings the multimodal capacity and agent-like reasoning. And now, in 2025, we have GPT-5 recently released, which has a very long context window and with advanced reasoning. And then especially at the current stage, we have some abilities like workflow or AI agent, this kind of thing, and MCPs. Probably we will talk about a little bit. Looking ahead, by 2027, we expect to see the reasoning-first AI architecture, AI-specific chips, and widespread development of autonomous agent. Looking further into 2016s, meaning for say, this may be the era of HI, which we call the general intelligence. However, I think the time and the implications are still open to discuss. Okay, so after the development, we have some key definitions about AI. First, here we have the artificial intelligence, but under this, machine learning actually is a kind of tools that we realize the AI nowadays. By the definition, it's a kind of AI approach where the AI system learns a function from data and make the prediction or decisions without relying on written rules. Okay, we can say that it will not relying on handwritten rules, but do this kind of thing automatically by learning from the data. So we can see the relation between the machine learning and AI. You can think AI as a broad one, and with the AI, machine learning is a key method to realize AI. And inside machine learning, we have the neural networks. And if this kind of neural networks is deep enough, we usually call it like deep learning. So some basics about machine learning. Just like we said before, first, it should have the training process to train a model from data, and then use this trained model, we can do the prediction or inference to estimate the new output from the new input. Okay, so for the machine learning tasks, it also have some clear classification between the supervised or unsupervised learning. Supervised learning means that we will give the labels, and unsupervised learning, it means that we will not offer labels. For this one, it's like supervised learning. Here is label what we give. And for the unsupervised learning, we just give the data, we just give the X, not a Y. So it's like unsupervised. Also, it has different kind of core tasks like clustering, regression, association, analysis, and classifications. For the classical machine learning, it typically relying on manual feature engineering. That is, the expert designs the features combined with statistics models such as SVM or decision trees, so it can work well with small data sets, training faster, and is more interpretable. Especially when we say this Paris rule, this more example of Paris rule, if we trying to fit the parameter C and the parameter M based on this rule, we can find that it's very, very explainable. So we can interpret it. Which does this fact mean, or which does this fact mean? So it's like we train the just like we train a physically model with AI algorithms, with classical machine learning algorithms. Also, we can sometimes, if we are not so sure about this kind of rule, we can use polymers. But for this kind of polymers, it's still somehow interpretable, but not so interpretable as this one. Okay, so this is like this is the classical machine learning. Apart from the classical machine learning, we have saw the power or deep learning recently. So it's like a multi-layer neural network, automatically feature learning. And it is very excellent at handling unconstructed data such as images, speeches, and natural language. However, it requires not labeled data set and very powerful computations. So also, unlike the classical machine learning, it becomes less interpretable, and it also requires longer training. Okay, for after this, we can see some classical machine learning algorithms. For the supervised one, we can say the simplest one is a linear regression. We use the NOT. Also, other kinds of fitting or regression, like polymers. Also, like GPR, SVM, naive Bayesian, random boosting, decision trees. This is quite important in computer science, just like in the age of 2000s. Okay, and for the clustering and association analysis, this is like we use some algorithms to group the data with out labels, just like the k-list, k-means, GMMs, PCA, SVD. All of this quite important in the classical machine learning, and especially before probably I think before 2010, this machine learning algorithms is quite popular in computer science. But after that, nowadays, we focus more on the deep learning. If we talk about deep learning, we have to talk about artificial neural network, ANN first. In the simplest form, form is like a network of interconnected nodes or neurons organized into the three types of layer. First, this is the input layer, and in the middle is the hidden layer, and this is the output layer. Each connection between the nodes has a weight, which determines the strength of influence from the one neutron to another one. Also, it has a BIOS, which allows the model to shift the threshold, improving the flexibility. It also have a what we call activation function. This is quite important to introduce the nonlinearity here. And it also has a loss function. Actually, we do the training or what we say the backward propagation almost based on this loss function to find the influence of different kind of parameters. So just as we said, talked about before, we have a training process and the user trained model, we can do the prediction. After this, we have the deep learning. Why we call it deep? Why it becomes deep? Here are some facts. As we can see in the previous one, it only have one layer that we call hidden layer. But for the deep learning, we have, for instance, for this example, we have 1, 2, 3, or a total of 3 hidden layers. So these layers act as a chain of feature extractors. The first layer captures low-level patterns, and then we have the middle layer to combine them into meaningful shapes or phrase, and then we have the top layer of high decisions, such as to identify an object or to answer a question. So with this kind of architecture, we have expressed powers. That is, the deeper the architecture is, the more power it can approximate much more complex functions with fewer parameters. So also, this kind of architecture is very adaptable because the features are learned. The same architecture can be applied to different domains with minimal manual changes. Of course, this pause only works with there is enough data. This is very important for deep learning. If we want to use deep learning, we must ensure that we have sufficient data on hand. Okay. For next one. Okay, for the deep learning, there are some very important architectures, just like the first one is a CNN, what we call the convolution neural network. It's mainly for the image processing. It has the process with a spatial layer we call the convolution layer, which use small filters to scan across the image. Actually, for this kind of filter, or what we call the canal, is used to track the feature of the image. And this kind of the parameter inside the canal can be learned from the data. So also we have the pooling layers to try to reduce the spatial size of the data by summarizing the nearby pixels. So this does not only speed up computations, but also helps to reduce overfitting by making features more general. And then we have the classification layers, including a flatten and including a FCN, we call the fully connected layer, and the softmax. With after these layers, we have the decisions about which does this image belongs to. It's a car or van or truck. It will output some probabilities to see. Just in this case, it shows that this one has a 19% of likelihood that is a car, but it also predict 8 percentage that it's a truck and 2% is a bike. So CNN has become a cornerstone in computer vision tasks because this combined computation with strong accuracy. We will also talk about this later, how it can be applied with a fatigue issue. And also we have the recurrent neural network. This kind of neural network is designed to process sequential data by retaining information from the previous steps. In engineering, this is important when analyzing the time series data from sensors. This is very important in structural health monitoring. For example, string, or vibrations can be recorded over times. This key features is time-dependent state transition, where each hidden state carries information from an earlier state. The most important one at the current stage is the transformer. It's like this one, a transformer, the famous cartoon. Actually, we call it transformer. By definition, it's a deep learning architecture based entirely on self-attention mechanisms. This is designed to process sequential data in parallel. You can see here, because if we also can do this kind of thing by Rn, but this one is by series. That means for instance, you have A, B, C. You must process A first, and then B, and then C. But for this one, it's in parallel. You can do A, B, C together. So, science order matters, positioning, coding, or sometimes we call embedding in computer science is added. So the model knows the relative position of elements. Especially it has a special architecture of encoder and decoder. Through this kind of architecture compared to RNNs, that is recurrent neural network transformer, can process data in parallel. This is very important, and it can capture the long-time relationship more efficiently and avoid something like grand vanishing or exploding issues, make them especially powerful for tasks like transmission, summarization, and more important, large language model. Actually, the T in GPT stands for the transformer. Okay, so also we have the GAN. What we call GAN is generative adversarial neural network. This kind of network is very important by definition. It stands for it's not so much a brand new type of neural network, but like a training framework. It uses computational components, a generator, which starts with random noise and tries to create data and it looks real, and a discriminator, what we call D here, the G and D. This is to create, and this is to judge. So by this, we can say that we can try to do something like for instance, to generate images, videos, or try to enhance our data set. So to be honest, the GAN, or what we call GANs, is not a strategy for training, a strategy for training rather than a network structure. Also, we have the PINEs, that is physically informed neural network. This is quite important for our engineering subject. What are they? A PINE is a normal neural network, but we embed the physics. You can see here the physical constraints, and also like a boundary and initial penalties on them into the loss function. So this is a loss function. And for this one, we have the physical term, and also the boundary and the initial term, and also we have a regulation term to control the overfitting here. So for this kind of architectures, it can be better for generalization because the physical acts as a very strong knowledge, prior knowledge. Also, we use this kind of term in Bayesian prior knowledge. So the model can extrapolates more sensibly and is less data hungry. So it can be trained on this data. It's more reliability because we incorporate physics. We can avoid non-physical artifacts. So it's also more efficient. Once trained, the inference is instant, and it so we always the training can be heavy, but use times we can try to reducing the data needs, improving the trustworthiness, and delivering fast surrogate that will still obey the rule of physics. This is very important. Also, we have the reinforcement learning. This is like unlike traditional supervising supervised learning, which relies heavily on label data. Reinforcement learning focus on learning from interactions. That means there is an agent, it interacts with the environment, and it learns from its interaction with the environment. Just like currently we can see this kind of thing very popular, just like this is a robot here try to play chess, and this is two robots fighting here. Actually, they are training the algorithm behind for their brain is like it's realized by the reinforcement learning, but we can see they are not so smart here, right? Because the algorithm is still developing, under developing, we can say that. So this feedback loop like state, action, reward is that what we allows reinforcement learning to success in robotics game playing like AlphaGo or some other autonomous system like self-driving. Actually, we do this by giving it punishment or reward based on the actions from the environment. Actually, for the case study one, we use the reinforcement learning to do something like the management planning. We will talk about it later. So, for the artificial intelligence, we have talked about the large language model. This is a very flashing frontier of artificial intelligence. So this kind of model is a type of AI that is pre-trained on massive data set. And then this pre-training enables them to learn the statistic relationship between the words and the phrase. And once after the train, it can generate text, translate language, write different kinds of creative content, and answer your questions in an informatic way. So this is like currently we are here for the natural language models. So overall trade has moving from the narrow task-specific tools to general problem solvers. Just like nowadays, we can use GPT-5 to solve some mathematical questions, but sometimes we don't say we cannot trust them because they are not so reliable. Even if now we have the GPT-5, it's still not so reliable. So short summary about different kind of machine learnings. Just like in case the GPR represent kinds of traditional machine learning, it can work with small data sets, it's interpretable, and it can quantify prediction uncertainties. It's like for the application, we can use it to predict the fatigue life on the limited test data. We can use it to do reliability analysis. Also, sometimes the probabilistic modeling of fatigue characteristics. Actually, we have maybe two or three or four works on this, but we're not going to share this today because due to the time limitations. Also, we have the CNNs for this kind of thing is strong in pattern recognition, especially for data like images, vibrations, and acoustic emissions. For instance, it can be used for damage detection for SHM images or feature extraction for fatigue clock injection or localization, just like we got singles from the AE acoustic emission. We can try to use this kind of text to do the feature extraction. And also we can have the RNN, what is a recurrent neural network. For this kind of thing, we can use it to do the fatigue clock prediction, especially in sequence, and also remain useful life estimation forecasting use long-term monitoring data. We can see here. So it's best for the SHM tasks. And also we have the transformer. This is super to the recurrent neural network for long sequences, and it's more robust or for multimodal data. Actually, we will show you with this with our second case study that we try to fuse SHM and SCADA data we get from the Winterbein for fatigue prognosis. Actually, this kind of data can be also used for adaptive operation and maintenance scheduling. And then we have the GAN, useful for data augmentation and generation where real fatigue data is scarce. Every time we do the fatigue analysis, we have to face the issue of lack of data. So this, I think, sometimes this can help if we can use this kind of GIN. So also we can have the points which can ensure the physical consistency. Just like the fatigue clock propagation modeling, we can try to embed some physical rules like Paris law into the neural network. We can also couple physics with the health monitoring data for more reliable prognosis. We can also use this to do the hybrid model for fatigue life estimation. What we talk about hybrid here is like half data driven and half physical driven. It's like a co-driven by data and also by physical models, because just like the physical models conveys the human knowledge. So for computer science, they always focus on the data driven, but for our as engineering, I may prefer the hybrid one because the knowledge is also very, very important. Also, we have the reinforcement learning, that is agent interacts with the environment by reward and penalties. We can use this for the to optimize maintenance scheduling or do some inspection planning or do control strategies for fatigue damage mitigation. Especially this is especially true for wind turbine structures, which we can adjust the operation of wind turbines. So if we time, we can share this in the future, because we recently have a work trying to use this kind of optimization algorithms to help us to reduce the fatigue issue in wind turbine towers. Also, we have the natural language models. This kind of thing we can use is pre-trained on massive data and fine-tune it for specialized tasks. And it can be used for reporting or maintenance, log analysis, or decision support chatbot for engineers, and literature mining for particular models. Actually, this is a direction that currently we are trying to work on, and hopefully we may have some progress in the near future. So some platforms recommended for machine learning, just like Python, PyTorch, NumPy, sometimes also SciPy and Pandas and Matplotlib. You can say all of this belongs to the Python, and also Jupyter. Yeah, right. Jupyter notebook is quite friendly to the new beginner. And also we have other platforms such as TensorFlow and OpenCV. And for Chinese platform, we also have this Panel, which is open. This one is open source, and so sometimes for some very simple machine learning tasks, we may also use a MetaNet. Okay, so we have talked quite a lot about the general perspective for AI tools. So I will just try to speed up in the next. So for how can we do with AI? In the recent years, I work on the topic of digital twins, especially digital twins for engineering. This can be supported by a list of AI tools. Just like with the AI tools, we can do a list of tasks. Just like this first one is a forward digital twins for geometrical reconstruction. Here we can see how a digital twin can be supported by AI tools for this kind of task. Just in case we use a drone to equip with the cameras or laser scanners to fly over a bridge or other structures. Then this data can be processed to generate highly detailed 3D feature models. And we can also talk about recent activities in nerve, that is neural radius fields, which allows us to reconstruct a 3D model from different 2D images from different perspectives. This result is a digital twin that accurately captures the geometry of acids. Uh, what's more, we can use digital twins powered by AI to do the tasks. That is for the digital twins from the node to state condition. That is condition assessment. First, we reconstruct. For instance, here we use videos to reconstruct the nodes on bridges with videos and sensor data. Also, we can sometimes construct it from the monitoring data. Then these nodes can be inputted into physical models. And then we can estimate what's the output of structure, and through incorporating some distortion models, we can do tracking, we can track the cracking or corrosion fatigue cracking process. Finally, we can have a probabilistic estimation on the fatigue damage goals. So after this, we also have a backward digital twins. Unlike the forward digital twins, this moving from the result back to the structure states. Instead of starting with a load, we began with the monitoring data. Actually, here we try to incorporate the production, monitoring, and inspection together by using the digital twins. Here we use the operation we use here is Pine and DBN, what we call is dynamic Bayesian neural network to perform the model data assimilation. This ensures us to update the key model parameters such as fatigue threshold in real time. So the updated model can be used to calibrate structural reliability and to refine the prediction of crack growth. And so you can see here, this is a continuous refine of crack growth. And then in this way, the digital twins continuously learns from the field data, ensure more accurate state estimation and reliable prognosis. And also, we can use the digital twins for the intelligent management, just like in this case. Reinforcement learning here used here to link actions, states, and reward to support the maintenance decision making. That is means when to do, what to do, or how to do, how if we do not, and how if we do it. So the system continuously evaluate these questions, balancing the risks, cost, and the performance, and also structure integrities. By integrating the mechanical models, digital twins, and then we do the planning, we can simulate different scenarios, optimize inspections and repair schedules, and automatically we can achieve provocative, cost-effective system management. So let's start our first case study, that is digital empowered inspection and maintenance of steel bridges. Here, we will go through background methodology, result discussion, and the quick takeaways. I will speed up a little bit because I saw almost one hour, right? So the case study focuses on steel bridge health, which corrosion fatigue is very important, is very prominent here. So the question here is the maintenance of health, especially for this bridge. There is a railway under the bridge. So for the maintenance, we only have limited time windows, just like 1 month or 2 months, or just 1 week ago, someone from the authority from the railway department, they will say that, okay, now you will have 2 hours window to do this kind of task. So with this very strong construct, we have to think about how to maintain the bridge properly. That's why we're trying to first to lower the state of the bridge by integrating the different kinds of data, and then we do the decision making using machine learning. Okay. So this is a methodology that is from simulation first and then to prognosis and then maintenance. Actually, first we do the node monitoring and we use finite element model, which is updated with the health monitoring data to transfer the node monitoring into the simulation of the stress spectrum here. And also we do the prediction of stress spectral by using the Bayesian dynamic linear model to predict what's its future. And also we incorporate the distortion model, and then we can have the prediction of its time variant damage. What's more important here, we incorporate a dynamic from DP that is called partial observable Markov decision process. Use this kind of model, we can incorporate both the distortion, prediction, and the inspection result here, and also effect of retrofit, all in one model. Within this model, we solve it by the reinforcement learning. That is an algorithm we call A3C. Solved by this model, we can do the intelligent maintenance. That is, we can estimate the risk and the cost, risk against the cost, and we can see the structure state here, and we can also update the structure state based on our inspections. What's more important, we can help to do the decision, just like you can see symbols here. These symbols means different kind of decisions for maintenance. We can do the decisions automatically based on the structural condition. So for simulation, this is a numerical modeling first, and then we fine-tuned it from the vibration data, that is vibrational measurement of the different data point. And then we use the monitoring traffic to incorporate into the updated model, and then we have the stress spectral, and we do the future inference, and we can have the prediction estimation on its current stage, on the history, and also prediction on its future. And also, based on this, we incorporate the TPSN, that is for the corrosion fatigue modeling of the fatigue damage. We can estimate the damage evolution. We can also estimate the reliability evolution. And from this on, we incorporate the dynamic from DP. That is the method we try. What's the innovation here is that we're trying to incorporate the monitoring data here, that is M node here. We incorporate this into the model. So that's why we call it dynamic, because this node in a traditional POM-DP, it's static, not dynamic, but here we incorporate the time effect here. So that's why we call it dynamic POM-DP. So we use penalty and reward to evaluate the maintenance actions. And also this is a way we incorporate the inspection results. We consider both the magnetic inspection and acoustic emission here. And also we consider the dredging and coating for the repair and the replacement. So as we said before, we use deep reinforcement learning to solve the dynamic POM-DP. And for the result, first we can say that DC, that means dredging and coating, is here. So we can say that this triangle lasts for the whole life cycle. So it is continuous because it can reduce the corrosion. And we can also say that AE, acoustic emission, is AE here, this one. We can say acoustic emission are suggested near the end of life, because if we want to do something like repair or we do something like replacement, it will cost a lot of money. So we must have a better understanding of its condition first. And also it suggests DC and AE sometimes. And it's like for the this is a critical hire. It suggests a replacement of around every 20 years, like that. It should be stated that this is automatically decided by the algorithm or the reinforcement learning model we trained here. Also, we can see the influence of data integration. Okay, we just do not have time to dive into details. So we can focus more on the strategy and the cost. We can see that different timing advised for different members. So this is a suggestion for different members throughout all different halves of the bridges. But however, we can see the similar model suggested for different members. Even some may be replaced by two or three, by four times, some two times or some three times like this. And we can see that the maintenance cost, inspection and maintenance cost becomes apparent after around 20 years here, given under the given condition. And we can see that inspection is very preferred, especially the AE, that is acoustic emission, which have higher accuracy. And we can see in the whole lifetime, it suggests a total of 16 replacement. Okay, we also try to incorporate the idea of opportunity maintenance. That is, do something by taking opportunities. That is means we can do something together so that we can save the money. So we can see that the inspection increased notably, and we can see the repair also increased, but slightly. We can see also the replacement increase, or only slightly, only increased by 2. We can see the action cost decreased very notably, or more than a half, because we can share the cost if we do something together. So some highlights. This means that digital twins enable intelligent maintenance specifically tailored for bridge hairs. We can also see that probabilistic deterioration prognosis performed by integrating production, monitoring, and inspection. And we can also see that dynamic POM-DP is quite powerful, which is the algorithm proposed here. And especially when we equipped it with a reinforcement learning algorithm SVC that we adapted to guide the optimal maintenance after prognosis after structural condition. Also some future suggestions. Based on this work, we can try to do something like the online and interactive digital twins. Also, we can try to incorporate digital twins with something like mixed reality robots and control devices. Sorry, excuse me. Do we still have time for the case study too? Or should we just talk about some final words here?
Well, at this moment, I would propose people to ask questions to the preceding part because of, well, originally it was expected we take it for 1 hour, which is quite approaching this limit. So
Okay.
if we continue, this will be edit time. So let's go on first with questions to the preceding part.
Oh, okay. Just being mindful. Maybe we can show a little bit for last slides. Show some extra, just like some of our engineering demonstration on this kind of text. Is this fine? Just this kind of thing. Is this fine? A few slides, like three to four.
Well, I will repeat again that now I would ask the audience first for the questions to the first part, and then
Okay.
we can repeat. We can proceed with the next second part. We can proceed with extra if the people will stay with us. So first, let's go to the first part.
Okay, sure.
If there are any questions to this first part.
Oh, I have a question. This is Adrian. So, related to this overall development, and actually it's just modeling, it seems to me that you skip a very important development step, which is verification and validation.
Yeah.
Without validating, okay, this type of modeling framework, let's say at the specimen level, at the coupon level, subcomponent level, you just cannot trust the data that you collect when you apply it to a bridge or an engine or whatever. So my question is, did you try, because there's so much data, and you can generate that data by working with a test facility. to use this framework and predict fatigue crack growth under certain loading conditions, or fatigue in general, which is much more complicated because fatigue is controlled at the grain level, and you don't have that information. So before trusting the data, because I wouldn't trust it if I were you, did you try it? Okay, run some experiments, get some data from literature, because there is, because I made use of it, and try to see how good is this framework.
Okay, Andrew. So, thank you very much for your questions. It's a very good question. Actually, for my personal experience, I work first on the material models of fatigue modeling, just like we try to do something based on the test data. But for the case study I present here is more about the inspection and the maintenance. So for the validation, what we carry out here is that we do the validation about the, let's see, maybe here. We do the validation of the bridge models of the finite element models here. That is, after the updating, we can see that the gaps between the test and the post-row model or alternate model becomes very minor here. You can see the green one. The green one is the design model. So after this, we can see that we can match the structural response of this between our modeling and our measurement. This is what we do the verification here. But in this work, at the material level, we do not do anything like the validation of the fatigue or corrosion fatigue modeling. But for this kind of model, we just use the one we developed from prior wells case study. Actually, I think that one has maybe has been submitted like maybe in 2019 or 2021. I just cannot remember clearly. So this is a already developed model for the material.
So let's go back.
Material.
Let's go back
Yes.
to that bridge slide.
Yes. Yes.
So if I look at that bridge, it seems to me that the final model is a beam model. This is something I would do 30 years ago. So by using a beam model, okay, it's a very simplified model, okay, with respect to this particular bridge. Okay, if I would have to validate in front of someone all this framework, I would do the following. I will stop the traffic on the bridge. I will put a bus in the middle. I will have strain gauges everywhere. Okay, I will take those measurements. And after that, I'll put that bus in motion, okay, to get vibratory conditions and compare again strain gauge measurements, okay, against the model. Put 2 buses, 3 buses, and so on. So if you have that kind of data that shows validation, not verification, verification is something else, validation of your model, okay, you have a story to tell, but I don't see that.
Yes. Actually, this is what we did. We use a vibration measurement here. That is, we have what we call a WIM system. That is weight in motion system on this bridge. We do not mention it in this slides, but in our paper we mention this in details. Actually, there is a WIM system here and here that can help us to record the traffic. And what's more important, here we have 2 cameras that can help us to reconstruct the traffic flows. So we can exactly know where is the traffic, what's the traffic. Actually, we also have other works that is trying to estimate the load on the bridge by integrating the video and the sensor data together. Yes, please.
So
sorry.
that's a frequency measurement. What I'm asking for is a strain measurement, okay, at critical locations. You cannot do anything with a frequency measurement in lifing procedure. You need strains that you can convert to stresses through a final model, and you can use that with whatever model you have. Okay, so those frequencies do not mean anything to me.
Actually, for this kind of thing, especially when we do hash monitoring, we rely more on the vibrational data. Just like frequency is a part of that. Actually, we rely more on the something we call the acceleration, because for this kind of thing, it can capture the global behavior. But if we want to go into the detail for the string data, if someone says they can have a very good agreement between their measurement and their prediction from finite element models, that's a big news. Because if you state the strain gauge just in front of some hotspot, the exact measurement will vary against the distance. So if we try to do the in that way, I cannot say it's not feasible, but it's somehow very challenging if you want to model some global behavior here. Hope this helps.
Okay.
Okay, please, are there any questions? Manjit, please, go on.
Yes, hello, everybody. Thank you for a very, let's say, overviewing project and to introduce the AI tools in engineering. I would like to continue with the question from Adrian.
Yes, please.
About the basics behind this model. You're let's say introducing some AI tools for getting an overview of the fatigue, for example, damage or maintenance strategies for a bridge or for a tower. In this case, what fatigue damage model did you use? Based on how did you calculate, for example, the fatigue, and how did you validate that? You're
Yes.
talking about damage factors and so on.
Yes. Thank you very much for your questions. I think probably maybe the colleagues for this workshop is mainly from fatigue domain. Actually, I'm also from fatigue domain. For this data, actually, it's a very simple one. It's like an improved version of ASA model, straight knife curves, like that. We just try to incorporate two factors. One is a P, that is a probability. Another one is a time, because if there is caution present, there will be the degradation of fatigue strength, right? So we try to incorporate the degradation of fatigue stress into this model. So after that, it becomes a TPS, and as you can see that this is a fatigue stress, and this is number of noting cycles, and this is service life. So it will change with service life. And for this model, it's not a new one. This one is what someone else already used, because for this task, we mainly focus on the management of fatigue issue or management of structural integrity. So for the fatigue cracking modeling itself, we do not give it so much focuses. So we use some existing models, and for this model, maybe in our work, like maybe in our work in 2019, I think that one is on construction, building material, or appliance science. I'm not so sure about that. We validated this model before when trying to validate another model that we proposed for the crushing fatigue modeling, but using the fractal mechanics. So for this work, actually for this work, it's more on the global scale, on the structural level. But if we want to try to apply artificial intelligence in some detailed works, just like we try to know what is crack growth, what is crack growth pattern, what will crack grow, what will crack just like merge it together. probably we will have some separated work. But for this one, it's like a global scale. Actually, to be honest, for the fatigue issue, the most important thing is we try to establish the relationship from micro scale to meso scale, or even to the structural scale. This is a very important thing. Actually, if we have time, maybe we can share some of this about our work in the future, because we are now trying to use the surrogate model to bridge these gaps. Hopefully, this will be published soon because we have already seen some positive progress in this direction. Hope this help.
Okay, thank you. Actually, I'm looking forward to your next case study, if we enough have time to see
Yeah.
what other possibilities are available.
Maybe if we have time, we can just
yeah, sure. It depends on the German.
Yeah. Yes.
Well, I have an issue because I promised some student to have a discussion with me, but I can keep the discussion and presentation running. And well, just if you decide to stop it, I mean to stop to finalize the meeting today, it will stop recording, so we can go on.
Okay.
Till 4.
And about the presentation, could we have the presentation as well?
Please go on. But just I will be not present. That's all.
Okay.
I will keep computer running. Recording will be on, and I will not be here. That's it.
Okay.
Thanks for the presentation. Yeah. Go on. Yeah.
I think we should set a limit as well. Is it okay to continue until 4 o'clock in 20 minutes? Jan?
I would be happy if this is in 20 minutes because then I need computer back. Yes.
Exactly. Okay, so I think.
So please, Junlin, 20 minutes more. Yeah.
Perfect.
Thanks.
Okay, maybe I will try. I will try to save the time. Just like I will try to finish it in 10 minutes or 5 minutes. Okay. So for the second case study is about wind turbines. For this case study, we're trying to develop a sustainable digital twins for deterioration wind turbines structures. For this kind of structures, it has more permanent fatigue challenges as the turbine gets large and also the speed increase and the heat of structure increase. And we can see that the feature is that this kind of structure is adjustable. We can try to adjust the operation of wind turbines. And we have the availability of multiple sensor data and numerical models. So what we do here is we're trying to estimate the structure stiffness and the loading frequency, the loading history together based on the sensory data and the what we say the operational data. This is a census we consider here. That is SCADA and some other sensors here. And also this is the framework. First, we do the perception and then the assessment and then the prognostic evaluation about the deterioration state of each component. First, we do something like the adaptive interpolation to enable the data fusion of sensor data from multi-source, including SCADA and SHM. And then we do we use a transformer to do the hybrid deep learning for load estimation. And what's more important, we use a reinforcement learning to do the joint estimation of nodes and model parameters together. So also we incorporate the Bayesian dynamic linear model, that BDLM we used in the last task. We use this to estimate the future state of structural spectrals here, also the structural conditions here. So here is the approach we use here. Hey, we do not consider the coercion issue, so we use the PS model, that is life circle. We use it to estimate the fatigue reliability of bolts. And in this framework, we can say that first we have the model updating. This is updated. We can say that it's almost very close to true, especially the DDPG. The DDPG method outperforms, it performs best. And also we can see the displacement before and after updating. We can see that after updating, it has better alignment here. This is before updating. And also we have predict the fatigue damage, and we can predict the reliability of this kind of bolts. So some key findings, we do the inverse computation by surrogate modeling to reconstruct loading history from system. This is quite important for our fatigue assessment. Also, we use a DBLM to estimate future loading development based on historical records. Also, we use the reinforcement learning here to estimate the model parameter and the loading history jointly. We also do the hybrid simulation, and there's some suggestion for this kind of tower. We should improve the fatigue resistance and use better construction, and more important, use smart operation and maintenance, or what we call the intelligence maintenance. Excuse me, or inspiration from digital twins-based poker losses to intelligent operation and maintenance. This is what we learned from this study, and something about actual, that is our engineering project and demonstration on this kind of tape. First, we have the platform for the intelligent operation and maintenance of offshore wind turbines. Also, for the bridges, we have a living bridge digital twin system. This is a platform. As you see, when we capture a car just passing the bridge, we can see the rate of the steel hairs, because it reflects the stress state. And after using this stress ranges, we can calculate its fatigue life. We can estimate the remaining useful life. And currently, we are also trying to use natural language model for engineering. I'm sorry, this one is in Chinese, is that we're trying to incorporate the knowledge we get from the digital twins into a large language model to let them act as an expert, a consultancy expert for site engineers. Also, we are now also trying to develop some metaverse issues, use some for industrial. What we call the industrial metaverse use a VR system. You can say the student state here is experiencing this kind of system, because for this kind of system, the true state of this kind of boats is from just like connections from the state conditional system from our digital models. And we can saw here for this kind of, we also try to use AR model. This is just a white wall, and we can see just like a virtual turbine here from the virtual reality of what we say the augmented reality here. So this just conclude on my presentation. For my work, it's like a joint domain between the civil engineering, game and planning, and the data science. If you have more questions, please kindly write me emails to me or find me on WhatsApp or my latest publications on my ResearchGate. And this is a code for my WhatsApp. Thank you so much for your listening. And if you have any further questions, I'm very glad to take. Okay, I think that's all my presentations. Sorry, excuse me. Just I'm not sure. I just cannot measure. Could you just open your mic by yourself? Because I think I just do not have a right to open that.
Thank you.
Yes, thank you.
So you're going to share your presentation with Jan, and it will be shared somewhere? Because I'm new to this group. I was just wondering how you're going to share.
So I think I have already signed the consent to share this presentation, right? Yes. Yeah, I think so. Yes.
The recording for this presentation would be uploaded to the YouTube. You can access there. I'll ask, and if possible, we can share the a presentation if Jandan has the consent to share this presentation with all the attendees today. So we can share this presentation to maybe LinkedIn or any other platform as well.
Thank you very much for your kind efforts.
No problem. Thank you so much, Jandan. Anyone, any of our from our audience have any question from Jandan, too? You can ask. I think there
So
is no question.
yeah,
Yeah,
probably if
please.
you have further questions, please kindly email me or just send me messages on WhatsApp, I think.
Thank you so much for your wonderful presentation. I would really thankful on the behalf of FABER and especially the working group 2.3. So we'll love to keep listening from you in the future as well. If you will have any other topic which you believe that can be a good asset for our group, you can just write me back anytime. So we'll arrange another meeting for you. And thank you so much, everyone, for joining today. I'm just going to conclude today's meeting. So just take care of yourself and have a good weekend a day after. Thank you. Take care.